Hello, welcome to a new video. In this video, we are going to discuss isomorphisms. We will discuss its definition. Then we will see some examples and non-examples. So first of all, before going to see the definition, let's analyze the word meaning of the word isomorphism. Actually, it is derived from the word isomorphism is derived from the two Greek words isos, which means same or equal, and morphe means form. Next definition of isomorphism. See, we want two groups to define an isomorphism. So the two groups are G and G bar. Let G and G bar be two groups, and we then consider a function mapping from G to G bar. A mapping, that mapping is phi. Phi is the mapping from G to G bar. And if this mapping is 1 to 1 and also 1 to 1 to 1 and 1 to, uh, and also it preserves the operation of phi of AB equal to phi of AB equals phi A phi B for every pair of elements chosen from the first group. Here here the operation is the operation in the first group, but on the right side the operation is the operation on the second group. So the condition, let's again state that definition, an isomorphism phi from the group G to G bar is a one-to-one mapping from G on to G bar, and that preserves the group operation phi of AB equals phi A phi B for all A pairs of elements AB in G. When there exists an isomorphism from G on to G bar, we say that G and G bar are isomorphic with each other, and we write that they are isomorphic with each other using this symbol. And G is isomorphic to G bar, it is read as. Next, we have to discuss some examples. Example 1. Here in this example, the first group is G is the group of real numbers under addition. And G bar is the positive real numbers. Here we consider only positive real numbers under multiplication. So in the first group we have the operation addition. In the second group we have the operation multiplication. And we define the function mapping from G to G bar as phi of x is equal to x square. 2 raised to x. Phi of x equals 2 raised to x. Clearly, phi is a function defined from G to G bar. Next, we are going to see that it is a one-to-one. This function is one-to-one, and for that, let's suppose 2 raised to x equal to 2 raised to y in the second group. Then, by taking logarithm on both sides to the base 2, logarithm of 2 raised to x to the base 2 equal to logarithm of 2 raised to y to the base 2, and then we get that simplifying that we get that x equal to y. So whenever 2 raised to x equal to 2 raised to y, we get that x equal to y. So phi is one-to-one. To establish that phi is onto, for we consider an arbitrary element of the second group, say y be any element of the second group. Then corresponding to this element in the second group, we can find an element, say x in the first group, such that phi of x equal to y. That's the question, whether it is possible to find an element in the first group such that phi of x equal to y. Yeah, you can see that it is possible. Why? Because if there exists an element x, then 2 raised to x must be equal to y. And then by taking logarithm on both sides to the base 2, we can free x, or we can find the value of x equal to logarithm of y to the base 2. Finally, whether it preserves the operation, for that we take x and y, two elements of the first group, and we take phi of x plus y. See, plus is the addition, is the operation of the first group. So phi of x plus y equal to 2 raised to x plus y equal to 2 raised to x into 2 raised to y, but that equal to phi x, 2 raised to x equal to phi x, and 2 raised to y equal to phi y. So phi x into phi y. So phi of x plus y equal to phi x into phi y for all x, y in G. And therefore, thus phi preserves the group operation. Okay, therefore phi is an isomorphism. But next example, it's not an isomorphism. We are going to show that a function which is defined from one group to another group, it is not an isomorphism. So it's a non-example for isomorphism. The mapping defined from R to R is the set of real numbers, which is defined by phi of x equal to x cube is not an isomorphism. The reason, first of all, you can check verify that it is one to one. The mapping is one to one. Phi is one to one because when we take phi x equal to phi y, that can imply that x cube equal to y cube, and directly it implies that x equal to y. But phi is and phi is one to also because phi of x equal to y. When phi of x equal to y, then x cube equal to y. Therefore, x equal to y raised to 1 by 3. Y raised to 1 by 3 is an element of R. Thus, there exists an element x in R satisfying the condition phi x equal to or giving us phi x equal to y. Again, when we verify, when we try to verify whether it preserves the operation, there it fails because phi of x plus y equal to x plus the whole cube, it can never be equal to x cube plus y cube for all xy belonging to R. So phi is not an isomorphism. So because phi does not preserve the group operation, so it's not an isomorphism. Next example, here we consider finite cyclic group of order n. See, any finite cyclic group of order n, it is then isomorphic to Z, and we are going to show that. How can we do that? Suppose G, the first group is a cyclic group of order n. Then, since it's a cyclic group, it has an element A that generates all elements in that group. Therefore, G is equal to the group generated by A. Hence, G can be written as elements of G can be written as E, A square, A cube, etc. to A raised to n minus 1. Moreover, A raised to n equal to E, A raised to n equal to E, and A raised to E equal to E. A raised to 0 equal to E. And the second group contains the elements, and these elements are classes of integers. Zn equal to class 0, class 1, class 2, etc. class n minus 1. And these, what is the nature of the first class, class 0? Class 0 equal to class 0 contains all those integers, both the positive and negative integers, which are multiples of n. But class 1 contains all those integers which are multiples of n plus 1. And class 2 contains all those integers which are multiples of n plus 2. And see, each integer is added with the 2. Yeah, okay, and that is the nature of the second group. So that also contains n elements, and we define a function phi from G to Zn by phi of actually correct this function. It's a change. So phi, actually it is phi. It is not f. I say phi of a raised to I, phi of a raised to I equal to class I, phi of a raised to equal to class I, and then clearly phi is 1 1 and on 2 because you can verify that it is 1 2 1 1 and on 2. It's very easy. Next, we can say that it preserves the operation. So phi of a raised to I, because phi of a raised to I, a raised to j equal to phi of here also instead of f, phi must be used. Phi of a raised to I plus j, and that directly becomes class of I plus j. But class I plus j equal to class I plus class j. Class I plus class j equal to phi of a raised to I plus phi of a raised to j. Therefore, phi preserves the group operation, and thus all the three conditions are satisfied, and hence phi is isomorphism. Okay, thank you for watching.